Hello everyone, welcome back to our course CSEC 513, Lightweight Cryptography for the Internet of Things. This week's topic is target devices and performance metrics. So today's topic will be based on NIST internal report 8114 titled Report on Lightweight Cryptography. So this talk and the slides are actually the highlights of this document. So for further read, I strongly recommend you to read the whole NIST report. So let's look at what NIST Lightweight Cryptography project is all about. In 2013, NIST initiated the Lightweight Cryptography project to study the performance of the current NIST-approved cryptographic standards on constrained devices. So they wanted to understand the need for dedicated lightweight cryptography standards because AES is the standard block cipher standardized by NIST. So if AES fits everywhere, then you don't need any lightweight cryptographic algorithm at all. So actually, this is NIST approach. So they say that you should use AES if you can, but if you cannot, then at that point you need lightweight cryptography. So they wanted to see if such a need exists. And if such a need is identified, they wanted to design a transparent process for standardization. So for this reason, NIST held 2 lightweight cryptography workshops. So the aim was to get public feedback on the constraints and limitations of the target devices and to identify requirements and characteristics of real-world applications of lightweight cryptography. So both industry and academia attended these workshops and helped NIST to have comments on these topics. So after these 2 workshops, NIST has decided to create a portfolio of lightweight algorithms through an open process. And in NIST internal report 8114, titled Report on Lightweight Cryptography, NIST aims to summarize the findings of the lightweight cryptography project and outline NIST plans for the standardization of lightweight algorithms. So far, they held 2 workshops at NIST in 2015 and 2016. So after that, they published this report on lightweight cryptography in March 2017. So after that point on, the standardization process is started and algorithms are submitted. They received 57 lightweight cryptography algorithms and 56 of them is announced as the first round candidates. And last year, just before this workshop, and due to the findings of this workshop, they announced the second round candidates, which were 32 algorithms. And currently, the 4th lightweight cryptography workshop is being held. But due to pandemic, this time it is virtual, and at the time of this recording, actually the workshop is ongoing, so you can still go to this link and register for the workshop and listen to the talks. And if I'm not mistaken, the updated timetable says that they are going to announce the 3rd round candidates in December at the end of this year. But of course, due to pandemic, this timelines might change. So let's focus on target devices. Lightweight cryptography targets a wide variety of devices that can be implemented on a broad spectrum of hardware and software. So this makes actually the problems kind of big because it is hard to design a standard that will be good on almost every hardware and software. On the high end of the device spectrum, there are servers, desktop computers, tablets, and smartphones. So these devices are really fast in terms of CPU, and they have huge amount of memory, and almost all of them comes with multiple cores. So we are not worried about these devices. So lightweight cryptography actually is not required here, but as we will be talking in the future, once you are going to use lightweight cryptography in small devices, most probably those devices are going to be talking to the servers or desktop computers. So you have to implement this lightweight cryptographic algorithms on almost every device. So conventional cryptographic algorithms generally perform well in these devices, so they don't require lightweight algorithms. But on the other end of the spectrum, there are devices such as embedded systems, RFID devices, and sensor networks. And lightweight cryptography is primarily focused on these highly constrained devices. Let's look at microcontrollers first. Microcontrollers are available with a wide array of performance attributes. Although 8-bit, 16-bit, and 32-bit microcontrollers are the most common, there are significant sales of 4-bit microcontrollers for certain ultra-low cost applications. And we mentioned this before because this is a cost-sensitive operation. If you are going to build millions of devices, you don't want to use a device of 32-bit microcontroller if you are not going to need it. So you need to go with a cheaper alternative if it fits your needs. A wide variety of instruction sets exist, which typically only contain a small number of simple instructions. So this is one of the problems for the implementation of cryptographic algorithms. Not every device, not every CPU, not every microcontroller has the same set of instructions. Even with the high-end computers, for instance, some CPUs or GPUs might have instruction for rotation, so you can rotate bits of, for instance, 32 or 64-bit word with a single instruction, but some CPUs won't support this instruction, so you have to use 2 shifts and then end operation to perform the rotation. So a rotation operation might need a single instruction for some device and 3 instructions for the other device. But when we go to very small devices like 4-bit microcontrollers, the instruction sets are really small. They have a small number of simple instructions. So even to perform a simple operation, you may need to perform a lot of instructions. This may result in a large number of cycles to execute common cryptographic algorithms, which may make them too slow or energy consuming for the intended application. This is particularly a problem when it is necessary to satisfy real-time constraints using a limited amount of energy. So that is one of the other problems. Having a lot of instructions would mean that you are going to consume more energy, and most of the small devices will be battery powered. So we need an algorithm that would fit these devices. For some microcontrollers, the amount of random access memory and read-only memory can be extremely limited. So when we compare to ourselves, our personal computers, the old ones like Commodore 64, those devices had 64 kilobytes of memory, but today we are having computers with gigabytes of memory. So we kind of assume that there are no devices with a small amount of memory, but in real life, there are many microcontrollers that has smaller RAM than a Commodore 64. So here are some examples. Following microcontrollers can have 64 bytes of RAM or less, going down to as little as 16 bytes of RAM. And here are some examples for these microcontrollers. Again, all of these are taken from the report from NIST. Let's move on to RFID and sensor networks. On the bottom of the spectrum, there are RFID and sensor networks, which are often realized in an application-specific integrated circuit in order to satisfy some of the most stringent implementation constraints. Of particular interest are ultra-high frequency RFID tags, for example, tags that are using the widely deployed EPC Global Gen 2 and ISO standards 18063. For RFID tags that are not battery powered, only a limited amount of power is available from the environment, and this is one of the other problems that we face in real world, because you need to perform cryptographic operations just by getting a small amount of power from the environment. Such devices require cryptographic algorithms that not only use a very small amount of gate equivalence, but also meet stringent timing and power requirements. Lightweight algorithms may be subject to various other constraints, a topic that will be explored during the first phase of the standardization effort. The aforementioned examples are therefore not intended to be an exhaustive list, but instead to illustrate settings where conventional algorithms cannot be implemented in order to understand the need for lightweight alternatives. So these words are actually from, again, NIST report. So as they mentioned, the report only gives the main idea. It is not an exhaustive list of devices or what we need. So this is the reason NIST is holding workshops and getting comments from the industry and academia. For instance, in the last year's workshop, the talk titled Cryptography in Industrial Embedded Systems, Our Experience of Needs and Constraints, is a good example for the idea behind the workshop and the comments that can NIST get from the industry and the academia. While lightweight cryptography primarily targets devices at the low end of the spectrum, it is important to note that it may be necessary to implement lightweight algorithms at the high end of the spectrum as well. As I mentioned this before, because in the Internet of Things, every device talks to each other. For example, many resource-constrained sensors may send information to an aggregator that, by most accounts, is not constrained. However, the aggregator must support lightweight algorithms in order to interoperate with the constrained sensors when they use lightweight cryptographic algorithms. In short, the environment and application need to be factored into the decision of whether or not conventional standards are acceptable. It is not just the limitation of a particular device that drives the need for lightweight cryptography, but also the other devices in the application that it directly interacts with. So this is really important. You have to decide if you need lightweight cryptography or not by considering the whole set of devices that are going to use